Now? Okay. So we continue with the second session of the day on isogenies and group actions. And the first talk is about radical 2 isogenies and cryptographic hash functions in dimension 1, 2, and 3 by Sabrina Kunzweiler, Luciano Maino, Tomoki Moria, Christophe Petit, Giacomo Pope, Damien Robert, Miha Stopar, and Jan Botti. And Miha is going to give the talk.
Yeah, thanks, Peter. Hi, my name is Miha Stopar. This will be a talk about radical 2 isogenies and cryptographic hash functions in dimensions 1, 2, and 3. And Peter already said who worked on this paper. Most of the isogeny-based cryptography is based on the problem that given two elliptic curves, it's difficult to find an explicit isogeny between these two given elliptic curves. And but in the last years, especially after the Castric-Decroux attack, there was a major shift towards higher dimensions. But what does it mean, higher dimensions, in the context of elliptic curves? It means that elliptic curves are geometrically the same as elliptic curve is the same as torus geometrically, but algebraically is given by this kind of equations. But when you go to higher dimensions, to dimension 2, or we also say genus 2 or genus 3 and above, so in genus 1 you have elliptic curve which is a torus, so that means an object with one hole, and then when you go to dimension 2, you have objects with 2 holes. When you go to dimension 3, you have objects with 3 holes, and so on. But the important thing is that this problem, which is assumed to be hard also for quantum computers, so to find an isogeny between abelian varieties. Abelian varieties generalization of this of elliptic curve. So the problem of finding the isogeny between the abelian varieties, it's still hard. Actually, even harder if you go into higher dimensions. So as an example of abelian variety in genus 2, it's one of such varieties can be given by this kind of equation, which is similar to elliptic curve equation, but the polynomial here is of degree 5 or 6. As I said, the problem of finding the isogeny is difficult, but if you are at some abelian variety and if you are able to choose the kernel, then of course it's possible to compute the isogeny and the codomain of this isogeny. But there are different techniques to do this, but these techniques are, some are less, some are more efficient. And what we did in our work is we came up with new formulas to compute an isogeny, given that you have a kernel, that you can choose the kernel. And as an application of these new formulas, we constructed a hash function. And just as an introduction into the field, I will just briefly present the history of hash functions based on isogenies. And the idea is that you have this graph of isogenies, of elliptic curves. So you have a graph where nodes are elliptic curves and edges are isogenies. And normally you take the isogenies of degree 2, so the isogeny which has a kernel with 2 points, which is called 2 isogeny. And then if you are at some elliptic curve, there are 3 outgoing isogenies, 2 isogenies from this elliptic curve. And you can do the random walk, so you consume at each step you consume 1 bit of a message. So if a message bit is 1, you take this isogeny. If the message bit is 0, for example, you take this isogeny, and the third isogeny is something where you came from actually. And you always start at the same elliptic curve, and the final elliptic curve is actually the hash of the message. Or more precisely, the J invariant of this elliptic curve is the hash of the message. So if the message is, for example, 0001, Then you take this path where minus is 0, so 0, 0, 0, 1. You end up at this elliptic curve. You take the J invariant as the message. Just as an intuition, why there are 3 outgoing isogenies out of the elliptic curve, I mean 2 isogenies, 3 2 isogenies, it's because you need to observe the 2 torsion group, and the 2 torsion group consists of 4 elements of the identity element, which is a point at infinity, and 3 other points. And then by choosing an isogeny out of this elliptic curve, it basically means you are choosing different subgroups of with 2 elements. So you can choose identity and P1 or identity and P3 as a kernel, and so on. So why is this hash message, hash function secure? It's as far as pre-image resistance is concerned, you should not be able to, given some elliptic curve or its J invariant, you should not be able to find the path, any path to this curve. And this is hard because it's actually, if you are able to find a path, that means you were able to find an isogeny between E1 and E2, and that's assumed to be a hard problem. And as far as the collision resistance is concerned, you should not be able to find 2 different paths to the same elliptic curve. So for example, this is one path and this is another path. But if you are able to find 2 such paths, that means actually that if you compose this path with the inverse of this path, you get the endomorphism of this curve, and this is again assumed to be a hard problem. So it's also collision resistant. So can we generalize these hash functions towards higher dimensions? Yes, we can, and actually before our work there were a couple of such constructions. The first one from Takashima in 2018. But the problem with this hash function was that so you need to be careful when you are composing 2 isogenies. And in this case, we are in the genus 2, so in the dimension 2. So we again observe the 2 torsion point, but in this case, it doesn't have 4 points, it has 16 points. And when you are choosing the kernel of this phi1 isogeny, you need to choose 4 points instead of 2 points. But when you are choosing then the kernel of this phi2 isogeny, if you choose the kernel in a way that this group intersects non-trivially with the image of this torsion group, then this is something that is called beta extension, and it can cause these problems. And actually, Flynn and T attack found an attack on Takashima hash function because of this. But then in 2020, Kastrick, De Croo, and Smith fixed this by taking a smaller graph, so just a super special graph, which is a subgraph of what Takashima used, and they used only good extensions, which means that the kernel of this isogeny phi2 trivially intersects with the image of this group, so it intersects only in one element. And then there were further improvements. So Kastrick, De Croo in 2021, they used multi-radical isogenies, which means the computation of the isogenies is faster. That's because traditionally when you are computing the isogeny out of this elliptic curve, for example, you are choosing the points that form a kernel of this isogeny, and then you do the computation. But if you have radical isogenies, you start with an elliptic curve and the point on the elliptic curve, and you have efficient radical formulas to compute the codomain of this phi, which has the kernel generated by P, and you also get computed this new point that is the kernel of the new isogeny, and so on. And this is more efficient. There is also a generalization of radical isogenies, which is called multi-radical isogenies. So basically it's the same, but instead of elliptic curve you have an abelian variety, and instead of 1 point you have G points where G is genus. And you have formulas to compute these new points that form a kernel for phi prime. And what we did in our work is we came up with new radical formulas to compute isogenies. But what we used is something that is called theta model, which is kind of an alternative coordinate system for describing abelian varieties. Essentially, you trade off this nice algebraic formula for elliptic curve with something much more complex, theta functions, which is much more complex, but surprisingly, the formulas that you came up, I mean, the formulas to compute isogenies are surprisingly simple and compact. So when you work with theta model, you work with theta structure, and we worked with a level 2 theta structure, which informally means how you label the two torsion points. And then you get theta functions, which you can evaluate on the points. And if you take the identity element and you evaluate with these theta functions, you get something that is named theta null point, in this case level 2 theta null point. And the interesting thing is that this null point identifies the abelian variety. So instead of J invariants, as from the beginning of the presentation, you can use this null point to identify the abelian variety. So for example, for genus 1, for elliptic curves, you have a point in projective space of dimension 1, which identifies the elliptic curve. And in genus 2, you have a point in the projective space of dimension 3, which identifies the abelian surface, and so on. But the question is, can and how can you do simple, efficient computation of isogenies using this theta model? And actually, last year, D'Artois, Maino, Pope, and Robert came up with a formula for the computation of the isogeny and for the evaluation of the points, which is surprisingly simple. So basically, you have an abelian variety and the theta null point that identifies this abelian variety, and you want to be able to compute the theta null point of the abelian variety B, which is the codomain of phi, and you want to be also able to evaluate the points. And their formula to evaluate some random point is it consists only of 3 simple operations: squaring, Hadamard transformation, and scaling. And Hadamard transformation is just a linear transformation. It's a matrix vector multiplication. So basically, to evaluate the point, you get the point on variety B. But what we used is the fact that here in this scaling step, for the scaling operation, it's used the null theta null point of B, or basically its dual. Its dual means that you apply the Hadamard transform on this point, and we use this. And the fact that because this is an isogeny, the isogeny maps the theta null point into this theta null point. So instead of a random point from the previous slide, we replaced this with a null point. And we observed the scaling operation at this step. And you can see that what it appears is this kind of an equation. And you can, given xi from this step, you can compute bi by computing the square root of xi. And then coincidentally, you also use the Hadamard at the last step because this is the dual, and if you do the Hadamard on the dual, you get again the original point. Yeah, our radical formula is similar to the work from the last year, but it uses square root computation instead of scaling at this step. And as an application of this formula, we constructed a theta CGL hash function, where the idea is pretty much the same as in the first isogeny-based hash function. except that at each step you don't consume only one bit, but you consume more bits. And basically, because here, because this is square root operation, you have for each coordinate you have two possible choices, and choosing different signs, meaning choosing different isogeny. So you consume a couple of bits, which defines these signs, and then you walk in this graph by choosing one of these isogenies. And the question is, why going to the dimension to higher dimensions if this was already possible into dimension 1? Well, the reason is, when you go into higher dimensions, the problem of finding the isogeny between two abelian varieties becomes harder. And for this reason, you can use smaller primes for the finite field. And this means that the arithmetic of the finite field is more efficient, and you actually get a speed up of because of this. And our Rust implementation actually showed that in genus 3, this hash function is the fastest, so it only takes 400 microseconds to compute the hash. And yes, with this I conclude my talk.
Any questions from the audience? I might have a quick question. So in these higher dimensional theta models, do you have an issue when you encounter products, or I guess in dimension 3 you can even encounter the product of an elliptic curve and a Jacobian, or product of 3 elliptic curves? Or do the formulas change then,
no? You can have problems, and actually some of the previous works had problems with this, but these radical formulas actually are the same, so it's kind of taken care of naturally.
Any more questions? If not, then let's thank the speaker again.
Thanks.
So the next speaker is Riccardo Invernizzi, who is going to present PRISM, signatures from large prime degree isogenies, which is joint work with Andrea Basso, Giacomo Borin, Wouter Kastrik, Maria Cortarea Santos, Altona Leroux, Luciano Maino, Frederic Verkauteren, and Benjamin Veselovsky. The floor is yours.
Okay. Thanks, Peter, for the nice introduction. Thanks for knowing all the names. I was a bit... as you mentioned, I will talk about how to create a signature scheme from large prime degree isogenies. But let's start from the beginning. What is an isogeny? So Miha already introduced a bit the concept. Essentially, an isogeny is just a map between two elliptic curves. But the catch here is that we're not really okay with any map. So we want this map to have a bit of properties. The first is, as you see here on the left, this map has to be defined by polynomials. So we want a map that take an x and y coordinate of a point, give us polynomial that define the x and y coordinate of the image point. And the other important properties is that it has to respect the group structure. So we are on an elliptic curve, we can add point together. This has to be respected by the isogeny. But these are essentially the only two properties that we care about. So once you have those two, you have an isogeny. An isogeny has points that are sent to 0. We call this the kernel. The kernel is the set of all the points that the isogeny map into the 0 of the image elliptic curve. And the size of this kernel is called the degree of this isogeny. This is another very important property of an isogeny because it tells us how the isogeny behave, essentially. And the degree coincides with the highest degree of the polynomials that are defined above. So for instance, the isogeny that you see there will be a 2 isogeny, or a degree 2 isogeny. And it will have 2 points in the kernel, and it will be a 2-to-1 map. So the thing on the right also coincides with that. So the degree will be quite important, and we will come back to that. There is a special kind of isogeny. An important one is called endomorphism, and is an isogeny that goes from a curve to itself. The easiest example is point multiplication. So you have a point on an elliptic curve, you can add it together like n times, and this is multiplication by n. This is naturally defined on every elliptic curve, and so this is an endomorphism because it's a map that goes from a curve to itself, is represented by polynomials, maybe not immediate, but it can be shown. So why are we interested in endomorphisms? Because they're a nice mathematical object. We can add them together because they're on the same curve. We can multiply them together because they act on the same curve. And these two operations are compatible with each other, so we really have a ring. And this ring is called endomorphism ring. And this is a very important property of an elliptic curve. So to every elliptic curve, you can associate an object which is called endomorphism ring. And as we've seen, multiplication by a number is defined on every elliptic curve. So in every endomorphism ring, you have z, which is the natural number that is naturally sits in your endomorphism ring. It's not the full story, usually. It's never the full story in the case we're interested in, but is always there. So that's a nice first step to understand the endomorphism ring. And the last introductory slide on isogenies, how do we represent an isogeny? So what it means that I know an isogeny. So as I said, an isogeny is just polynomials. And this is the most natural and the most classical way to represent an isogeny is by showing the rational maps or the polynomials that correspond to this isogeny. This map can be derived explicitly. It's easy to evaluate once you have this polynomial. You just take the x and the y of your point, and you get the x and the y of another point. And the complexity of this evaluation is polynomial in the degree, as a mathematician would say, in the sense that if I have a polynomial of degree n, the complexity of evaluating this is some function of n. In cryptography, we rather say that this is exponential in the size of the degree, which is the same, because if I have an n-bit degree, then it's exponential in n to evaluate this, but it's really the same thing. Another way, which is more recent and is what Miha's talk was about, is using interpolation data. So it turns out that if I give you the image of an isogeny on 2 points, which can not really be any point, but we can think of that as any 2 points. If I give you the image on those 2 points, then you can evaluate the isogeny on every other point. And this is kind of how interpolation works. There are 2 caveats. First, this requires evaluating the isogeny first. So I need to know phi of p and phi of q, and then I give them to you, and you can all compute this isogeny, but I need to evaluate it in the first place. The evaluation procedure, given these 2 points, is a bit more complicated, but it's kind of known how to do that. And the good thing is that this is independent of the degree, or almost independent of the degree. I'm cheating a bit here, but if you have a high degree isogeny, you can still efficiently evaluate it in this way, often. And so why are we interested in isogenies in cryptography? Why do we care about them? It turns out that we have 2 hard problems that are also essentially equivalent with each other, which is compute the endomorphism ring for a curve. So the object that I defined before, you take a random curve, you compute the endomorphism ring of this curve. This is very hard. And this is also related to finding a collision in the hash function that Miha defined before. And then you have computing an isogeny between 2 random elliptic curves. I give you 2 curves. You have to produce an isogeny between these 2. This is also hard. And on the other hand, we have some easy problems. So computing the endomorphism rings for some special curves that we know, that is easy. Given the endomorphism ring of a curve and an isogeny between 2 curves, compute the endomorphism ring of the second curve. That is also easy. And the way it works is you essentially carry it around with the isogeny that you have. And the last thing that is easy is compute an isogeny between 2 curves of which you know the endomorphism ring. So if you know the endomorphism ring of both curves, then you can compute an isogeny between them. As soon as you miss the endomorphism ring of one of the 2 curves, you cannot do that anymore. So how do we create some cryptographic scheme or like cryptographic hard problem from these hard and easy problems that we have? We start from a special curve of which we can compute the endomorphism ring. Then we compute a random isogeny. And this is, again, essentially what Miha did before. So we compute this random isogeny, and we carry the endomorphism ring of the first curve that we know to the second curve. So now we end up with a random curve that we can give. This is our public key. But we also know the endomorphism ring of this curve. And nobody else can compute it because this is a random curve, so it's hard to compute it. And this is essentially how all isogeny-based signature work. So this is the way the secret is generated. Now we're still left with a problem. How do we prove to someone that we know this endomorphism ring? And this is a problem that is solved, for instance, by SkiSign using Sigma protocols. So we generate the curve, the secret key and the public key, as I said. We commit to a curve, and here the procedure is essentially the same. Then the verifier generates a challenge. This is another random isogeny, but this is public. So the verifier doesn't know the endomorphism ring of the public key, so it cannot carry it around, so it can just compute a random isogeny and then publish this isogeny. Now we know the endomorphism ring of EPK, and so we can carry it around this isogeny, which is public, to the challenge. So now we know the endomorphism ring of the commitment, the endomorphism ring of the challenge. We can compute an isogeny between the two. And we are the only one who can do that, because this requires the endomorphism ring of the public key. So if we can show this isogeny, then we know the endomorphism ring of the public key. So this Sigma protocol proves knowledge of our secret key. Now, the good thing, the reason why people love isogenies is that signatures are very, very short, much shorter compared to any other post-quantum candidate. The drawbacks are that the signing procedure, as I show, is quite complicated. It has a few steps, is not very fast. This is getting better, but still is a bit slower compared to other candidates. And so today I will present a new hard problem. This new hard problem is computing a large prime degree from a random curve, a large prime degree isogeny from a random curve. So first thing that we're interested in, this becomes easy if we know the endomorphism ring of a curve. So this is the perfect trapdoor because it shows knowledge. If you can do that, it shows knowledge of the endomorphism ring of a curve. Little caveat, large and prime are both needed because, well, if I have to compute a small isogeny, that's just computing a degree 2 polynomial, so I guess everybody believes that we can do that. A smooth isogeny is also easy because if I have a 2 to the something isogeny, I can just split it as a polynomial into n 2 isogenies, but each 2 isogeny is fast, so I can do as many as I want. So this is also easy. So we really need large and prime degree. But once the degree is large and prime, we really believe this problem to be hard. So believe it or not, mathematicians have been computing isogenies for decades, and nobody found a better way than what we have today, which is, as I said, exponential in the size of the degree, or like linear in the degree, the mathematicians would say. We really believe to be hard, first for that reason, but then an argument maybe, yeah, mathematicians maybe are not very interested in efficiency, so they usually consider like 37 a huge prime. So what if there is actually a more efficient way that's just not known because people didn't care about? It turns out that also cryptographers have looked into this problem. So this problem is hidden in the security proof of SkiSign. They didn't find a way around it. Other schemes like PKC are limited by this problem. So if we could solve this problem more efficiently, the cryptographic field of isogeny would really grow and really benefit from that. So people really looked into this. So now everybody believes that this is the best we can do. And so how we build a signature scheme from that? Turns out that this is quite simple because, as I said, if I can compute such an isogeny, then I know the endomorphism ring of the curve. So it's very simple. You get a message, you hash it into a prime. The size of this prime is what defines security and efficiency. But yeah, you just get a prime of the correct size, and then you compute an isogeny of that size. Once you can compute the isogeny because you know the endomorphism ring, you can produce interpolation data for that. So you can publish the images of this isogeny, and then everybody else can verify that this is a correct isogeny of the correct degree. So as simple as that. If you compare with SkiSign, we don't have this Sigma protocol, commitment and challenge. This is just hash and sign, and is like the description is very simple, and this has a lot of benefits. It's much easier to analyze. It can be used, and it's already being used in more advanced protocols. So there are ongoing works for use this in advanced cryptographic protocols, which are very hard to build on SkiSign because of its shape. And also efficiency-wise, we will see that we can gain something there. So concretely, how much does it cost to attack our scheme? Key recovery is as any other signature scheme based on isogeny because the secret key is the same, it's generated in the same way. And so we have attacks that are roughly square root of p. So we have to take p, which is 2 lambda, where lambda is the security parameter. Forgery, so the best way to compute an isogeny of degree q, costs q square operations. And this means that our a, our security parameter for our hard problem, we can take it to be lambda over 2, where lambda is the security parameter, so it's very small. But, there is a but, if we take our prime, so our hash, to be lambda over 2, then we have hash collisions in lambda over 4, which is not something we're okay with. So we're forced to take a to be 2 lambda. And this is purely because of the hash function, which is both a nice and a bad thing about this scheme, is that, so if someone finds a better way to compute isogeny, so if someone finds an attack against our hard problem, we're kind of covered for a bit, because the sizes that we have are much more secure than what we would need for our hard problem. On the other hand, it means that we're kind of losing something. So if we could really get this to work with lambda over 2 of the size of our prime, then it would be much, much faster than ski sign in any possible way. But yeah, the hash is there, and so we have to respect it. Last remark is that the problem is not just computing an isogeny, but computing an isogeny after having seen a few isogeny of high degree. But this most likely doesn't help, because an attacker can already create high degree isogeny from the public key as long as they are smooth. And the fact that now they see also prime degree isogeny most likely doesn't help, because high degree isogeny are just harder to deal with. So they already have access to high degree isogeny. So this shouldn't help. And this is an assumption already, as I said, in ski sign and other places. So this really doesn't seem to work. So concretely, how big is our signature scheme? Signatures are 12 lambda bits, where lambda is the security parameter. To give you an idea, this is roughly 1,500 bits for level 1, which is 190 bytes. So yeah, it's quite small. It's the same compared to like most other signature schemes. Ski-sign to D West has some compression techniques, so it's a bit shorter. But yeah, it's roughly the same ballpark. We can also do a bit smaller, but then it becomes slower. The speed, we implemented it on the Ski-sign to D West C code base that is now submitted to the NIST level 2 competition. And compared to Ski-sign to D West, signing is 1.8 times faster, and it can actually become much faster. We can gain like 30 to 40% because we have some subroutine that are not optimized, like some LLL, some not isogeny routines that are not optimized at the moment, so we can do even better than that. Verification is 1.4 times lower, and that cannot be better at the moment. We don't know a way to make it better. But yeah, so overall, we can say we're faster. If someone cares about verification, maybe Ski-sign is a bit better, but again, it's very comparable to Ski-sign. So to conclude, we introduce a new hard problem, which is computing large prime degree isogeny from a random curve. And this, we use this to create simple isogeny-based signature, a new isogeny-based signature that is much simpler than Ski-sign and then other scheme. Performance and size are comparable to Ski-sign and the other scheme, but we get for free that we can create more advanced protocol using many more situations and more advanced constructions from this new hard problem. So that's it. Thank you, and I'll leave the floor to questions.
So any questions from the audience? Alex?
Yeah, thank you very much. You had on slide 13, you discussed security. I guess this is all classical security, right? Can you say something towards quantum? Are there speedups for quantum then?
Yes. So key recovery, quantumly, you can expect to have like Grover kind of speedup, not much more than that. But then there you have memory issue. So this is, so key recovery, we have the same prime size as Ski-sign, which is in the NIST competition. So yeah, we didn't do the analysis there, but other people did that for us. So there you don't gain anything. And in computing isogeny, there is essentially no speedup expected because it's just evaluating polynomials. So there is no quantum speedup known there. So yeah, hash collision is the same. So if you, depends on how you evaluate the, so now we take 2 lambda for collision resistance, but that's like, all the other like key recovery and hash collisions are studied like outside our common problem. The only new problem that we introduce is forgery, and there we don't expect to have any quantum speedup, so it's not known.
And for hash collisions, it should be then more like a third root like claw finding algorithm.
Yes.
Then would that matter?
Yeah, then it depends on, because this this Grover algorithm doesn't include the cost of memory. So I don't know. I'm not quantum expert, so I read that people say, yeah, now we believe that AES 128 is still secure, and the same reasoning should apply here, right? Because this is 256 bits, so the cost of memory should compensate for that. But yeah, I'm not. This discussion. So I think it's not settled even in the quantum community. I'm very far from a quantum expert, so we just take what is written elsewhere and we apply it. But yeah, if someone then says, yeah, hash has to be bigger, then we just make it bigger. And this is the same for key recovery and everything else. But this is not that we have. So the only problem that we introduce doesn't have any known quantum speedup. So everything else can be analyzed by people that really are already analyzing it, and then we will just take the results. But for now, this is what we found. So
yeah. Thank you.
Thanks.
Hello, thank you for your talk. So just now you showed that Prism's hash and sign structure is simpler than ski sign's identification protocol. But could you give any intuition for why then Prism's verification is slower?
Yes, so this is a bit technical. So essentially what you have is this interpolation data here, right? So this interpolation data, the cost of verifying it is just, you take the interpolation data, you turn it into an isogeny. And this is the same for us, for ski sign, and for essentially everything else. And the verification is only that. Okay, so it's independent of everything that comes before. So when I show this is how you generate the signature, but then you publish the signature, and computing, then verifying the signature is just computing that isogeny. So it turns out that ski sign has a nice way to pre-compute part of this chain that you have to do at the end, and that is what saves some time there. So the size is the same, the size of the signature, the size of the point is the same, and so in principle we have to do the same amount of operation, but ski sign does a bit of this operation in the signing already. So you spend a bit more time in signing, and you save a bit more time in verification. Now if we could do that, our verification, our signing would still be faster than ski sign, because overall we do less operations. So if we could do that trade-off, it would be faster, but we didn't find a way to do that, because of this structure, ski sign can like save something there, move something to the signing, and that's a very nice feature that we're trying to do the same, and then we can get the same speed of the verification and the faster speed in signing. But yeah, we didn't find a way, so for now that's the reason why is lower at the moment.
Any more questions? Do you have a question? Okay, I have a short question. So since this is a slightly more flexible construction as well than ski sign, have you thought about like building more advanced protocols from this framework?
Yes, I think there is. I know that there is some ongoing work about some like threshold signatures and things like that. I don't know. Maybe other people are also doing that, but there is already some ongoing work, and there are some results. So we can do some constructions, more advanced constructions. It's not published yet, but yeah, there is some work on that.
And maybe one very short question related to what Alex asked. So you have this thing. What makes you choose like a bigger prime or bigger Q is this like collision thing, but I guess this like square root thing has also like a large memory cost.
Yes, exactly.
So couldn't you move into a regime where you lower this Q, or I think it's probably Q a little bit, so that it's still the memory becomes infeasible in practice?
Yeah, we worked a bit on that. I think now A is slightly less than 2 lambda, because one thing that is not mentioned here, but when you hash, you have to do primality testing on the result of your hash. So that's extra cost that an attacker has. So also you can save a bit, like some bits there. This kind of thing we worked a bit on, but it's in the end it is not. It just makes the security assumption a bit more fishy, and you don't gain significantly much. So this is all in signing, and our signing is really much faster than, for instance, key sign. So we're kind of okay there. Unless we find a significant way to just ignore hash collisions, which of course you cannot do, but like you have to find a way. And then we can go back to talking about forgery, which is Q squared. Then the gain is significant, so order 4 thing. Then it would be worth playing again a bit with the hash function, just make, I think, in my opinion, a bit more fishy. But of course, you could do that. You could gain some bits there, I think, using these memory arguments and such. But it's probably not be a significant gain. So that's why we decided to leave it clean and simple.
Okay, then let's thank the speaker again.
Thank you.
Okay, so the next talk is by Jonathan Eriksson, who is going to talk about faster scallop from non-prime conductor suborders in medium-sized quadratic fields, also with a lot of authors, which is joint work with Bill Alembert, Jean-François Bias, myself, Chris Leonardi, Aurel Page, Renate Scheidler, and Marton Todbagi.
Yeah, thanks for the introduction. Indeed, the title is quite long. It's not the abstract, if that was any confusion, but yeah. For this talk, I kind of wanted to talk a lot about kind of the context of our work and the previous things that led to it, to give an intuition for what exactly we're trying to do and what exactly we're trying to solve. And then for details in how we're doing it, you can look in our paper. So, of course, let's start at the very beginning. Everyone knows the Diffie-Hellman protocol, but I just want to fix a bit of notation and a bit of weird colors, maybe. Well, the point is that we're going to talk about group actions, and we will, of course, generalize this to group actions in a minute. So, fix some cyclic group of order P generated by H, and Alice and Bob will consider their secrets to be random invertible elements mod P. Okay. And yes, as I said, the reason I'm using this notation is because I want to generalize to group actions. So probably we should define this. We already had a talk on this on Monday, but yeah, so I guess by now everyone was there on Monday, so everyone knows what a group action is. But there's a couple of more properties that we would want. And one is commutativity, which code-based group actions does not have, so that's kind of what separates these isogeny-based ones. And another property that's useful for building cryptography is free intransitivity, which essentially says that you can go from any two set elements by a unique group element. Okay. Essentially freeness is the important one because you can always get transitivity by working in a specific orbit, which will actually become relevant later, but it's kind of a detail. So the first example of a group action is, I mean, if you haven't seen it before, it's maybe a little bit confusing, so it's good to think a bit about it. But we use the same H as before, our cyclic group of order P, but then we completely forget that it's a group. We forget that we can multiply the elements, and we consider our sets to be the generators of H. So in this case, just every non-trivial element. And then the group acting is invertible elements mod the order simply by exponentiation. Okay, so should think a bit about that, because if you get this example, then you really see that Diffie-Hellman is really just an instantiation of a more general protocol, where you fix some kind of commutative group acting on a set, and the secret elements are group elements, and then what they send are set elements. You apply your action and then send this corresponding set element. Okay, now of course this is exactly the same, so what in the world is the point of doing this? Well, the whole point is that this thing on the left is a little bit more general, which means that the corresponding hard problem is hopefully really harder, okay? So obviously the discrete logarithm based on the example I just mentioned reduces to vectorization, which is like the group action version of D-log. But D-logs, of course, there's a quantum algorithm, as everyone knows for solving this in polynomial time, while for vectorization, there's only sub-exponential algorithms. So right now, it seems like vectorization is really harder, okay? So the reason for another reason for doing this, of course, there's many ways to do key exchange post-quantumly, but the fact that this protocol is now so similar to Diffie-Hellman means that we get very direct analogs of lots of other more complicated protocols in the post-quantum settings by moving from group exponentiation to group action. Okay. So a little bit of this history of commutative group actions in cryptography. The timeline I will cover looks something like this, and the first part will be essentially what led to maybe the most famous group action protocol still, which is C-side, and that's indeed what I will focus on. So this will really be a very fundamentally different group action than the one example we just looked at. And okay, this maybe if you haven't seen these things, it looks a bit scary at first, but we will cover all of these separately. The group you're acting with is some kind of class group, and there's a set of certain elliptic curves, and there's some action that we will look at. So indeed, the 20 minutes is not enough to talk about this properly. So I just want to do a quick example so that people get a feeling for how these things work. And a class group, it's some kind of group you can construct from a ring like this, set adjoined some square root of a negative number. For instance, you can, of course, do it much more generally as well. But the point is that the elements are ideal or ideal classes. So the group elements can be represented by ideals of this ring. So for instance, in the one example I computed here, there's 6 group elements, and they can be given these representatives. There's the trivial class, so the principal ideal, and then the other representatives are the ideal about 2, 3, 13, 17, and 23. And then the group operation is also very simple. It's simply just doing, multiplying these ideals together. So if you start with a trivial class, you multiply by this ideal, you of course end up there. And then slightly less obvious, if you apply this or multiply by this ideal again, well, you would think that you get an ideal of norm 9 or something. And yes, you do, but that ideal turns out to be equivalent to this one, and I want to stick with these representatives. So, okay. And you can keep going, and you'll see that the group structure of this thing is a cyclic group of order 6. Of course, in cryptography, this 53 is indeed a huge prime, maybe, but we will use even bigger primes, slightly bigger ones in practice, but yeah. So now we'll look at this set, and I've phrased it kind of weirdly, maybe, but that will make the generalization again easier in a minute. So our set consists of certain elliptic curves, okay, well, defined over some fixed prime field. And then all such curves, they have a very special endomorphism. So Ricardo luckily talked a lot about the endomorphism ring. And there's one special endomorphism called the Frobenius, which just takes the coefficient and raises this to the pth power. And then my requirement for the set elements is that this Frobenius should satisfy a very specific quadratic equation. Namely, it should square to the minus p, which means that if I apply this thing twice, it will be the same thing as multiplying a point by minus p, or scalar multiplying, okay? And now to connect this to the class group, which might not be immediately obvious, again, luckily Ricardo covered the endomorphism ring, and now it's kind of clear that simply by sending the square root of minus p to this pth power Frobenius for our set element, this will be a ring injection, okay? So now we at least have some kind of relation between our group, which was the class group of this thing, and our curves or our set elements. Okay, and again, the action, I won't really go into a lot of details, but we'll just do a quick example. But the point is that to a ideal representative, so some kind of ideal in our class group, we can very naturally associate a certain isogeny by using this ring injection that I just mentioned. So for a quick example, we can start at the curve on top here, and then act by the ideal above 2. So this will be some isogeny of degree 2. I hope everyone paid attention during Ricardo's talk, because he introduced a lot of the things that I forgot to introduce, so that's good. But yeah, so some simple isogeny to evaluate something of degree 2, and you end up at this curve. And now you can repeat the procedure from here, and you'll see that you end up back where you started. Okay, and you can do the same thing with the ideal above 3. You end up over here, do it 2 more times, and okay, we're at the same place as when we applied the ideal above 2. And yeah, you probably see where this is going. You can do it 3 more times, and then end up back where you started. So this looks suspiciously similar to our group structure, and that is, of course, not a coincidence. The whole point is that indeed this class group acts freely and transitively on our set. Okay. Now there's a very fundamental problem with Seaside as I described it now. Because, well, Ricardo just spent 20 minutes talking about the hardness of computing large prime degree isogenies. So this means that ideal representatives, while their corresponding isogenies are going to be of degree equal to the norm of your representative, which essentially means that you need a very smooth normed representative of your group element if you just want to do Seaside. Okay. So the way Seaside fixes this in practice is that you don't sample random group elements. You instead fix a nice basis of your group. So your group can be cyclic, but you just fix a bunch of generators either way, which are easy to evaluate. And then you essentially act by vectors, well, R tuples of integers. And then the corresponding group elements is just raising your generators to the corresponding powers. Yeah. And then now the point is that we can indeed evaluate the action of this vector whenever it has a small norm, right? Because it's just applying these guys that we said we could evaluate essentially. And that's good for Seaside because that is enough for key exchange. But whenever you, I mean, as I said, the whole point of this group action framework is that it's easy to construct more advanced protocols. And you run into this issue that whenever you try to construct something more advanced than key exchange, or not, I mean, something else than key exchange, this turns out to be a huge issue usually, and essentially completely breaks your whole protocol immediately. So that brings us to our next timeline paper. Yeah, I should have probably mentioned that since it's not in the title, the thing we introduce is indeed Pearl Scallop at the end there. So all of these are previous works. So the next one is this Seafish protocol, which is indeed constructing some group action-based signature. Okay, but that's an example of another thing that just instantly break if you try to apply Seaside directly. So here the idea is that you want to turn this type of restricted group action into an actual group action. Okay, and the way you do this is a straightforward idea, but yeah, yeah. Well, anyway, the fact is that okay, the thing that we use now, acting by vectors, is because you essentially have some kind of surjection from Z to the R to your group, exactly by the map I just mentioned, sending the basis vector to each generator. Okay, and now the idea is that we want to compute the kernel of this map. Okay, and there are multiple ways to do this, but one simple example I gave is essentially just computing a bunch of discrete logarithms. And if you manage to compute the kernel of this map, then you realize your group as Z to the R modulo some kind of lattice. Okay. And now, how does this help you? Well, okay, let's talk. First, let's say we have fixed this. So again, an important point here is that this is really part of the parameter generation. You only need to do this once. But yeah, compute a bunch of discrete logarithms in your group to get this kernel lattice, and then compute a reduced basis of it. Okay, of course, expensive stuff, but you only need to do it once. And then now we want to evaluate a uniformly random group elements, so something that looks like D0000. Of course, D can be the size of the group, so it's going to have a huge norm. But because you have computed a reduced basis of your kernel lattice, you can solve the CVP problem for this E. Okay. And by definition, this F that you computed, well, it will be in the kernel lattice, which means that it acts trivially. So instead of evaluating E, you evaluate E minus F, which has small norm because it's the CVP solution. Okay, and the effect of this is indeed that C-side for the lowest considered parameter set can be made unrestricted. So you can use it as a proper group action for this specific parameter set. But now the problem, again, is that, well, the first step here was computing a bunch of discrete logarithms. So in specifically, you certainly need to know the class group structure. And this turns out, I mean, in practice, this is a very hard problem, actually. So for the lowest level parameter level, this was computed by some record-sized class group computation, but it's completely infeasible to do this for larger parameters. And as I said, there's this sub-exponential attack, so the general consensus is that this level doesn't actually offer any post-quantum security. Okay, so then we need some kind of new ideas, and that's indeed what Scallop did, and where our paper also fits in. There's one slight more generalization that I need to do again, and that is considered more general orientations than just this given by Frobenius. Okay, so you have this endomorphism ring, which consists of isogenies from the curve to itself. And essentially, one fact of life is that every one of these endomorphisms will satisfy some kind of quadratic equation. So you can simply fix one, and then you will get some kind of ring injection from a different imaginary quadratic order into your endomorphism ring. This is called an orientation, and then there's some kind of technical condition saying that it should be primitive, but let's forget about that for now. And now the intuition should be that essentially nothing changes, okay? You still have a free and very almost transitive group action on the corresponding set again. So it's not transitive, it's gonna have two orbits, but it doesn't really matter. You just fix one orbit and work in that one. And yeah, as I said, nothing really changes, so you can kind of do C-side still. But what is the point of doing this? The point is to work with a very specific orientation, because certain class groups are much easier to compute than others. So for non-maximal orders, something like this, computing the class number reduces to computing the class number of the maximal order, okay, and then kind of factorizing this conductor, but we can fix it to be primed. And that's what Scallop indeed does. And now you have some kind of thing where you actually can compute the class number again, even for higher parameters. So that's good. You can repeat the C-fish construction. Okay, so yes. But there are a couple of issues. Now that your orientation is not given by Frobenius, you need to have some kind of isogeny you can actually evaluate. And this is, now you need to use the general techniques that, again, Ricardo talked about, which essentially means that you need some kind of generator of smooth norm. Okay, and so we again have this issue where finding this is, of course, hard. And something I kind of swept under the rug here is that computing the class number can be much easier than computing discrete logs in the corresponding class group. So F should preferably also have certain properties as well. So actually, even though generating parameters for Scallop is slightly easier than for C-fish, it still doesn't scale very well because you still have kind of the same issues. Well, not exactly the same, but yeah. Okay, and the second issue I wanted to mention is that to understand what kind of situation we are in when we're working with Scallop, you have to look at this series of like these isogeny volcanoes, which are popular. So basically, you're going to work down here on these curves, which is essentially our set. Those are oriented by this thing. But all of them are going to be, you know that all of them has an F isogeny to a very specific curve, namely the curve oriented by z adjoint square root of -1. Okay, why is it the curve? Well, there was a free and transitive action, well, almost transitive. And this thing, of course, has class number 1, so there's only one curve on top. Okay, and now the point is that you can completely break Scallop if you can somehow manage to find a representation of this S isogeny, F isogeny, from F, which you know, and E0, which you presumably also know. So those are essentially the issues that we solve in Perl Scallop by considering slightly more general orientations. Okay, we don't fix the thing on top to be square root of -1, but we allow it to be square root of minus d, where d is now kind of like aptly chosen so that it's big enough so that you're completely clueless what curve is on top, but also small enough that we can compute the class group. Okay, and another thing is that we move from using large prime degree conductor to sort of a product of large primes conductor, which also gives more flexibility. And it turns out that if you do this, you essentially have exactly enough flexibility so that you can generate parameters where the norm of your generator is specifically 2 to the e, which is essentially the best you can possibly do, like the fastest isogeny, and e is not of too large size or anything. And indeed, as I said, there was this problem where you knew which curve was on top in Scallop, but now you have no idea. So that's of course not. I have to be precise here and say that like Scallop is not broken or anything. It's just that it's a very natural attack strategy, which seems a bit fishy, which you luckily don't have in our parameter set. Okay, so we implement this in C++ and compare it to Scallop and this Scallop HD, which I haven't mentioned, but is essentially a different version of Scallop. And you can see that it's already on the existing parameter sets. It's a big improvement, and we can also generate higher parameters that they were able to generate before. Okay, so 11 minutes to evaluate what group action element. Not even an isogenist could argue that this is practical, but it's at least a step in the right direction somehow. Okay. So the last word I wanted to mention is something that Ricardo also mentioned, and it's kind of, if you're very updated on the literature on group actions, there's kind of an elephant in the room, which is this new protocol, Pegasus, which came out very recently. Which at first glance seemed to kind of knock these Scallop versions out of the park in terms of timings. But, okay, so one reason it's very, very fast is that you no longer actually need to compute the class group structure for evaluating random group elements, which is very nice. But, as I said, the point of group actions is to create a bunch of like direct post-quantum analogs of existing protocols. And for certain MPC protocols, I think specifically those based on like secret sharing principles, you do actually need to know the class number still, okay? And the thing about Perl Scallop is it's not really about the actual protocol on how to evaluate elements in terms of these vectors and so on, which you want to move away from. But essentially, our thing is about creating curves with a nice, suitable orientation for cryptography, okay? And Pegasus works for general orientation, so indeed you can and should use Pegasus together with Perl Scallop if you somehow need to have this extra property, which you may usually don't need, but for some protocols you certainly need it. So yeah, this is not part of our paper or anything. I just wanted to mention that indeed it's possible to combine these two and meaningful in some cases as well. Okay, thank you very much.
Okay, any questions from the audience? Yep.
Hey, so if you had the ability to calculate this group structure, say for instance with Shor's algorithm,
yeah,
would it be preferable to just go back to good old C-side instead of adding all this structure?
Yes, so indeed, if you do have a quantum algorithm, or if you do have a quantum computer, sorry, indeed you can do, and probably should do, for the parameter generation. Okay, let's look at that again. For the parameter generation, you can and should use it to compute step 1. And that helps a lot. Okay. Now there's kind of another elephant in the room here, which is step 2. And that part, computing a reduced basis of L, is not even easy with a quantum computer. So this puts very high restrictions on the size of your kernel, that is. So the number of generators you can use. But that part becomes not even easier with a quantum computer. But a quantum computer would help for step one at least. I mean, if you want to use it with something like Seaside.
Okay, and a follow-up question is, do these primitives exactly instantiate group actions so that they are plug and play in all settings, or is it like Seaside where it's still restricted somehow?
No, yeah, good question. No, so all of these Scallop versions, indeed, they are really like kind of the perfectly modeled group actions, where you really can evaluate random group elements. But yeah, good question.
Any more questions? Okay, then let's thank the speaker again. So the last talk in this session is by Massimo Stuzzi, and he's going to talk about multiple group action D-logs without precomputation, which is joint work with Alexander May. Okay.
Thanks for the introduction. Hi everybody, so this is indeed in joint work with Alexander May, and we're both from Bochum. So let's start off with a real-world example. It is usual practice for both security and efficiency reason in elliptic curve discrete log to choose and fix an elliptic curve and use it as a standard. So let us assume we have company X that wants to publish a curve and make its user, like customers, to use it as a standard. So let us also be positive and assume that this curve was not backdoored and it's honestly generated. Then we have a result by Schubs from 1897 that says that there's a time lower bound to compute to solve discrete logs on this curve, which is the square root of the size of the curve. So even if the curve was actually honestly generated and not backdoored, company X could still do malicious things, such as precomputation attacks. And so just I'm gonna give you a naive example of a precomputation attack. So company X, even before publishing the curve, could compute and store the old curve on a lookup table, then publish the curve, and upon receiving an instance of the D-log, just look up the corresponding D-log in the lookup table. Of course, this is very inefficient, both in terms of memory and time, but in 2018, Corrigan, Gibbs, and Kogan proved that company X can do much better. So indeed, company X can invest in pre-computation time and to the 2/3, then publish the curve, and upon receiving an instance of the D-log to solve, just solve it in time and to the 1/3 instead of to the square root. So now that we have this small example in mind, I can tell you a bit more about how usually pre-computation attacks are structured. So they are usually divided into phases, the pre-computation phase and the online phase. So in the pre-computation phase, company X wants to perform a typically heavy instance-independent computation that should produce an hint. And then in the online phase, company X should leverage this hint upon receiving an instance to solve faster. So just to fit the previous example into this picture, in the previous example, instance independent, the computation must be instance independent, which means that shouldn't depend on the particular instance we're trying to solve, but rather on the general structure of the problem and, for example, on the specific elliptic curves that company X wants to publish eventually. And the hint in that case was the lookup table, of course. Good. So we all know that discrete log is not quantum resistant because of Shor's algorithm, and a natural generalization that carries over a lot of nice properties from the discrete log are group action discrete logs. And a natural question is whether the attacks and the algorithms for the discrete log can also be extended and generalized to the more general setting of group action discrete logs. So, for example, we hope that Shor's algorithm cannot be generalized to the group action discrete log. And so in this paper, we
we tried to address the question whether pre-computation attacks can be extended. Good. Now let me give you some basics about group action. Maybe I will go a little bit quicker since we've already had them. Okay, we need any set X in which we also want to fix a distinguished element, which we will call origin, and then also a finally generated abelian group. So yeah, it has to be commutative, not like in codes. And also we're going to call by G1 to Gn the generators, and also we assume that the size of this group is capital N. Then I can already define what a group action is. So again, it's simply a map from the Cartesian product of G and X into X that satisfies these two properties, the identity property and the compatibility property. Now I want to give you already an example. So we can take as X a finite cyclic group generated by H, and also we fix the origin to be the identity of the group, and also its cardinality to be capital N. Then the group G, that is gonna be the group that actually acts on X, are the integers modulo N. And then we have this action. And here I'm saying that this example is kind of special because X is itself a group. And this is actually not required in general from the definition of from group actions. Okay. Now I want to tell you a bit more about my definition of GAD logs, which is essentially vectorization from the previous talk. And to do that, I need some notation. So for an integer vector v, I'm going to write bol g to the v, just the product of the gi's to the vi's. And I want to recall you that the gi's are the generators of the group. And I'm going to denote by lambda, big lambda, the kernel of that sends an integer vector to bol g to the v. Then the group action D-log problem is given one element in the set X, find an integer vector such that that element can be written as bol g to the v acting on the origin, modulo lambda. And we require modulo lambda because, as also discussed in the previous talk, if you have such a solution to the GAD log problem and you add an element from lambda, that will still be a valid solution. So we want like some kind of uniqueness modulo lambda. And also we're going to restrict ourselves to the nice case of Fourier transitive actions, for which this problem is always well-defined and also has a unique solution. And these group actions are actually called also like more compactly regular group actions. And it happens that the example that I gave you before is actually a regular group action. And what is also nice is that the group action D-log problem for this action is the usual D-log. So also in the previous talk, we had a way to phrase the D-log problem as a group action D-log problem. This is just an alternative way. Good. Now I'm ready to give you our results, so our contribution. So we could extend successfully the pre-computation attacks from the D-log problem, for the D-log problem, to the more general framework of group actions, and both in the single instance and multi-instance setting. And also, we designed a new multi-instance algorithm without pre-computation for the group action D-logs, which actually comes out as a natural corollary from the multi-instance with pre-computation algorithm. And since I told you that you can phrase D-logs in terms of group action D-logs, this also directly yields an algorithm for like a multi-instance without pre-computation algorithms for D-logs. Good. So we can jump into the action, and I'm first going to describe the pre-computation phase of the single instance with pre-computation algorithm. So we start with the origin X, and we take a randomization step. So by acting on X with bol g to the R1, which is just a random integer vector, and we land on X1. Now from this point on, we want to perform a memoryless walk using the action. And memoryless means that the next step only depends on the currently visited vertex. So now the next step will only depend on X1. Right, so we might land on X2, and we want to repeat this process n to the 1/3 times, where n is still the size of the group. And we get to an endpoint. Now, just to ease a little bit the notation, I'm going to drop the ball G and keep just the integer vectors. And I'm also going to denote by v to the 1 the sum of all these vectors. And I'm going to label the endpoint of the walk with the corresponding x element, of course, and the sum of the vector that we used to get from the origin to the endpoint. Okay, now in the pre-computation phase, we want to repeat this process n to the 1 over 3 times. So we do it again and again. And the pre-computation phase ends here, and as a hint, we will only store the list of endpoints with the corresponding vector. Good. Now we can switch to the online phase, in which we're given an instance of the group action D-log problem. So we're given y1, and we want to recover w1. Now we can perform memory-less walk again from y1. And let's for now assume that this blue walk, this online walk, collides into the one of the pre-computed walks. Then by the memory-less property, when two walks collide, they will stay together, because a collision means that two walks visit the same within the same vertex, and since, like, by the memory-less property, the next step will only depend on the currently visited vertex, and so they will visit the same vertices on and on. So if the blue walk is long enough, it will eventually hit one of the endpoints. Let's say the last one, for example. And now I want to show you that having such a collision as in the endpoints, which we can actually efficiently detect at each step of the blue walk. We can just check whether we have hit one of the endpoints. And if we have such a collision, this collision directly yields the desired D-log, GA D-log. Indeed, we have two ways to write the same X element. By just equating them and inverting the action on one side, we can recover W1 modulo lambda. Good. So until now, we were just hoping to get such a collision. But in the paper, we proved that with such parameters, so if you do n to the 1 over 3 walks, and each of them is long n to the 1 over 3, and you save just the endpoints, and then the online walk is as length upper bounded by n to the 1 over 3, then you can actually solve the instance of the D-log of the GA D-log with constant success probability, because you can find this collision with success probability, with constant success probability. Now we can compute together the number of steps for the pre-computation phase, which is just the number of walks times the length of each walk. So it's in total n to the 2 over 3. And the space is just the size of the list of endpoints, which is just n to the 1 over 3. So you can kind of see that the memory-less property gives you a way to compress all the data that you stored, that you gathered during the pre-computation phase into just the endpoints. And then the online phase is just the length of the blue walk, which is roughly n to the 1 over 3. Good. Now we're ready to go to the multiple instance setting, in which we assume that we know that we are given, that we will be given n to the 1 over 4 instances. Then the pre-computation phase is exactly identical to the one in the single instance setting. The only difference is now we can afford to do slightly less long walks. So every walk is long n to the 1 over 4, but slightly more walks, so square root of n. And now we go to the online phase, and we're given the GA D-log instances we want to solve. And from each of them, we again do perform memory-less walks and hope that they collide into some of the pre-computed structure. And again, the memory-less property ensures that when two walks collide, they will stay together. And so if the blue walks are long enough, they will eventually hit one of the endpoints again. And I've shown you before that such collisions directly yield the desired GA D-log. Right? And we have a similar theorem in this case, for which we can solve all the instances with constant success probability. And again, we can compute together in a number of steps. The precomputation is n to the 3/2. The space is n to the 1/2, and the online space and the online time and the online number of steps is expected n to the 1/2. Good. Now we are on to the last step, which is the multiple without precomputation algorithm. So first, I'm going to give you a naive algorithm. So if you have, for example, an algorithm that solves a GAD-log problem in times square root of n, and you have m instances you want to solve, you can just repeat this algorithm for each of the instances and get runtime m times square root of n. However, what we have observed is that if you take the multi-instance with precomputation algorithm that I've just described, and you try to balance the online time and the precomputation time, then first of all, it is not actually, it is not a precomputation algorithm anymore, because you can, in spirit it is, but you can think of, since the precomputation time and the online time are the same, you can think of it as an online-only algorithm. And then what you will get is that the precomputation time is square root of m times n. The space is kind of optimal already because you have to store the instances anyway. And the online time is, again, as the precomputation time, square root of m times n. So you can, using our reverse theorem, you can solve all the instances with runtime square root of m times n. So we eventually have gained a square root of m from the naive attack. And if you think of m as quite large, then this is a huge improvement. Okay, eventually we wanted to test our results, and we did it for Seaside, which we know from the previous talk. And so we observed quite a discrepancy between theory and practice, because from the theorem we got that our success probability of the online phase, so the probability that we actually get such a collision, it's lower bounded by 1/8, and which means that on average you have to repeat the online phase like 8 times. And in practice, we actually observed that you have to do it once, more or less. And on the left side, you have the bit size of the class group, which is the group in the group action underlying Seaside, and on the right, the number of runs of the online phase. And this is because our proof technique really uses generous estimates, and we generously and pessimistically lower bound the probabilities. Great. Just to summarize, we extended the pre-computation algorithms from the D-log setting to the more general group action D-log setting. And we also have a new multi-instance without pre-computation algorithm that comes out naturally as a corollary of the multi-instance with pre-computation algorithm, which also allows for a very simple analysis. A free analysis, because we already did the analysis for the with pre-computation one. And also we observed that in practice this technique performs much better than what we can prove with our theorems. And that's everything from my side, and I'm ready to take questions.
Any questions from the...
Yeah, so I'm going to ask the obvious question. It's like, do you get similar scaling for Kuperberg's quantum algorithm? Do you think?
These techniques are inherently exponential because you don't have like a quantum counterpart, a counter correspondent.
No, so yeah, so there is the sub-exponential algorithm, and I was wondering if you know of any or have a suspicion that there might be clever ways to sort of speed up for the computation of multiple instances there as well.
Yes, and I don't think so. At least not with this technique, because it's inherently exponential. Like you have to kind of cover a huge portion of the set X with your action, then you might use introduce Kuperberg algorithm as a subroutine to solve some of the instances, and then maybe spread the knowledge you have of one instance to other instances. So this is another technique that was used to achieve a multi-instance without pre-computation algorithm. But this is still already the first part of covering a large portion of the set X is it's inherently exponential. So
yeah, that makes sense. Thank you.
There's no direct way to use these techniques combined to Kuperbergs.
Okay, thanks.
Any questions? And I have a small question. So since there was a talk a couple days ago about non-commutative group actions, and for that there's no Kuperberg, so have you thought about the non-commutative counterpart of this?
Actually, we talked about it, and I think we came to a conclusion that that couldn't be directly applied, but it happened quite some time ago, so I should think about it again.
Okay. Any more questions? If there are no more questions, let's thank all the speakers of the session. And I guess there's lunch break. Okay.
Thanks. It was yours. I like yours.